Today on How It's Made. Navajo rugs. There's an interesting report looming about these. Crude oil. Well, we'll be digging for black gold. Kaleidoscopes. It's all smoke and mirrors. Well, just mirrors, actually. And titanium dental implants. We'll be filling you in with the facts. But first, rug weaving is a traditional art practiced by the Navajo, a Native American nation located in the United States. They originally wove blankets and clothing for themselves. Then in the early 1800s, they began weaving rugs for sale, making home on the range just that little bit more comfortable. While many weavers create contemporary designs, Navajo rugs typically feature bold geometric patterns. The wool preparation and techniques developed by the weavers' ancestors have been proudly passed down from generation to generation. Everything in a Navajo rug comes from Mother Nature, starting with fleece, raw wool sheared from a sheep. Working one handful at a time, the weaver removes the mats and tangles and places the wool on carders, which are wooden paddles with metal teeth. By pulling one carder against the other, she straightens the wool fibers, lining them up in the same direction. This prepares them to be spun into one continuous strand of yarn. After 3 or 4 pulls, she flips the carders to straighten the fibers on the underside. She then rolls up the fleece and adds it to the other rolls in the spinning pile. She spins the fleece one roll at a time with a traditional spindle that she lays against her thigh and rotates towards her with one hand. This movement twists the carded roll of fleece into a strand. When she reaches the end of the roll, she connects another and resumes spinning, and keeps repeating this process until she's produced one long continuous strand from about 50 rolls. She then respins the strand to thin it out to the final weaving size. When she's done, she checks the entire length of the strand, pulling on thicker areas to thin them out, so that the entire strand is a consistent size from one end to the other. Here you can see the difference in thickness between the first spinning and the second. To infuse her wool with colour, she prepares natural dyes: sunflowers for yellow, walnuts for tan and brown hues, and cactus bugs for bright red. These bugs are cacti pests. She soaks the bugs in warm water overnight. Then she submerges them in a pot of water, pours in the pre-soaked water as well, and simmers for 45 minutes to an hour and a half, depending on how vibrant she wants the red dye to be. Meanwhile, she soaks the yarn in warm water for at least half an hour to open up the fibers so that they'll absorb the dye. After wringing out the yarn, she immerses it in the pot of hot dye and simmers for at least 45 minutes, depending on the amount of bugs, water and wool. She stirs frequently to ensure it dyes evenly throughout. It's the same process with plant dyes, except that she doesn't pre-soak the plants before boiling them in water. The shade of colour depends on the ratio of plants to water during dye preparation, and also of the dye to the quantity of the wool. Sunflowers and walnuts are just 2 of many plants the Navajo have traditionally used to produce a rainbow of dyes for their textiles. With her wool now spun and dyed, the weaver picks up her weaving comb and gets to work. Navajo ancestors used trees as the sides of their looms, but today weavers make looms from wood or metal. After stringing tight vertical lines of wool, called the warp, she uses a flat handmade stick, which is called a batten, and pries a wide enough opening through which to pass her hand with the coloured weaving wool. She weaves horizontally, in and out between the warp, first in one direction, then in the other. Then she packs down the wool tightly with her comb, so that the warp doesn't show. She inspects the emerging unique pattern, occasionally counting vertical strands to calculate the symmetry, a signature feature of traditional Navajo rugs. So there you have it. We've told you all there is to know. Crude oil, also called petroleum, is an unprocessed oil found deep in the ground. It forms naturally from decomposed prehistoric plants and animals. The colour can range from clear to black, the consistency from very watery to very thick. But it's always expensive when it hits the pumps. Oil companies who drill wells install pumping units to draw up the fluid that contains crude oil and salty water. This oil field in Central California, USA, has 6,000 producing wells. The pumping units can run 24 hours a day. Here's what goes on inside the well. With each downstroke, the pumping unit pushes a steel rod down the steel tube lining the well. With each upstroke, the rod rises, and the pressure difference between the fluid on the outside and the fluid on the inside opens a ball-shaped valve, plugging the bottom, letting the fluid flow up the tube. Another valve at the top releases the fluid out of the well. To drill a new well, workers first erect a drilling rig at the site, then hoist a giant pipe with a drill bit on the end. They feed this drill pipe through the center of a spinning disc, called a rotary table. As the table turns, the drill pipe turns, its weight bearing down and boring a hole through the ground. Once the drill pipe descends its full 9-meter length, they connect another pipe. The process is repeated with subsequent drill pipes until they bore into the reservoir containing fluid. Throughout the drilling process, they pump a mud mixture down the drill pipe. It comes out the drill bit at the end, hits the bottom of the hole, then backs up to the top. This process brings back the drilled out rock. After lining the well with a steel tube to keep the walls from collapsing inward, they mount the pumping unit and install the valves we saw in the model. The pumping unit pushes the rod up and down through the wellhead at the surface. As a safety measure, workers take readings to check the air for any hazardous underground gases that may be exiting the well. Once they determine the area is safe, they draw a sample of fluid to test the well's water to oil ratio. The typical ratio is 90% water to 10% oil. The fluid from each well exits via a pipe, and the pipes from all the wells feed a main line, leading to a gas removal vessel. The fluid contains carbon dioxide, hydrogen sulfide, and natural gas, which has to be extracted. They naturally rise to the top of the vessel and exit via a pipe which runs to the company's gas treatment plant. There, equipment removes and treats the hydrogen sulfide, transforming it into sulfur, which a local farm buys to use as fertilizer. The natural gas and carbon dioxide, meanwhile, are piped to another area, where they fuel the company's steam generator. The generator boils the water extracted from the fluid to produce steam. The company injects steam into the wells to heat the fluid, thinning it so that it flows faster. Once gasless, the fluid is piped to the treatment plant, which extracts the salty water. In this big tank, appropriately called a free water knockout, the separation of oil and water happens naturally, the oil floating to the top. To speed up that process, they add a chemical called an emulsion breaker. The extracted water exits via a pipe leading to the steam generator. The oil goes to a clarification tank, in which a chemical process filters out sand, which the fluid brought up from the reservoir. By the end, when the ratio is 98% oil to 2% water, the crude oil is ready to sell. Built-in meters give instantaneous water content readings. As an additional quality control measure, the company also draws samples for analysis in its own lab on site. In fact, they test throughout production to ensure sufficient water is being extracted at each phase of processing. Companies buy crude oil as a raw material for producing petrol, asphalt, plastics, crayons, perfume, and many other products. So there you go, yet another refined report from How It's Made. Coming up, don't ask me to stop jawing, I can't. It's a report on dental implants. And we show you what happens when coloured beads and objects collide with mirrors. It's definitely worth looking into, a veritable kaleidoscope of facts. See you after the break. Conceived in the early 19th century by a Scottish scientist studying light, peer inside and witness dazzling geometric images produced as mirrors multiply objects. Brought to us almost 100 years before another Scot invented the other tube showing dazzling moving images, called TV. The images are spectacular and fleeting, each one lasting just a second before the next appears. Many years after its invention, the kaleidoscope is still an eye-opener. To make a kaleidoscope, this craftsman starts with a mirror sheet that has an adhesive backing. He scores it to create long and narrow rectangles and gently breaks it along those score lines. This mirror's reflective coating is on the front instead of the underside. A mirror like this produces sharper reflections than a regular household mirror. He slices the adhesive backing to separate the mirrored rectangles. He snaps off the scored ends, creating perfectly linear edges. Next, he peels backing from a strip of blackout felt paper and wraps it around a glass rectangle. This felt-wrapped glass will be the third wall of a two-mirror system, one with a triangular configuration. He removes the adhesive film from the mirrors, then builds the triangle with the mirror's reflective surfaces facing inward, towards the felt-covered rectangle. This arrangement will reflect objects to create a circular image known as a mandala. He aims the mirror system at a light box with a two-line drawing in it. One line is curved and the other is straight. Peering into it, he adjusts the alignment of the mirrors until the lines morph into a 5-point star. This means the corners of the mirror triangle are precisely 36 degrees, and it's multiplying images correctly. He hot glues the mirrors and applies metal tape to the top seam to complete the kaleidoscope mirror system. In the art department, they assemble decorative objects against a black background in an acrylic cell. With every placement, she checks the effect through the triangular mirror system. She glues dichroic glass onto the backdrop. It's a kind of glass that's been treated and appears to have different hues. Other objects include jewellery parts, coloured wire, buttons, and even paper clips. She doesn't follow a specific design, letting her creativity run free. While she glues some down, she leaves others loose to simply tumble around inside. A sprinkle of tiny beads completes the grouping. As the mirror system multiplies these objects, they will create the mandalas. These are photographs of actual mandalas, and they'll be used to decorate the outside of the kaleidoscope. An acrylic adhesive is added to the rim of the cell, then a clear lid is pressed onto it. The lid fuses to the cell body, but it's not yet completely sealed. There's a tiny hole in the side of the cell, through which he now dispenses heavy mineral oil. Submerged in oil, the objects will float and move through the cell for greater effect. He plugs the hole with an acrylic adhesive and screw. Now it's time to assemble the kaleidoscope. He slides the mirror system into a heavy cardboard tube and cushions the mirror system with foam, and this stabilizes it. He then installs a metal eyepiece and a glass lens on one end of the kaleidoscope tube. Then slides the object cell into a protective metal cage that rotates. A transparent glass disc goes over the cell, and he applies adhesive to the cage, then inserts the assembly into the other end of the tube. This kaleidoscope is now ready for a viewing. Light passes through the object cell, illuminating the trinkets. Reflections bounce off the mirrors to create one spectacular illusion after another. 2 centuries after its invention, it may not be YouTube, but it is your tube, and it can give you a right old eyeful. The ancient Mayans hammered seashells into their jaws to replace missing teeth. That probably hurt. Those seashells were likely the first dental implants. Today, titanium tooth implants fill the gaps nicely, and of course, they're screwed in, not hammered. In the middle of the 20th century, it was discovered that titanium is a metal that bonds with bone. It revolutionized restorative dentistry, making enduring tooth implants possible. To make these implants, they start with a solid titanium rod. This 4-meter rod will be used to make more than 200 implants. The technician inserts the rod in a long holding device, which keeps it straight as it feeds it into a lathe system. The titanium rod spins as computerized tools slim it down and cut threads into it. These threads will help anchor the implants in the patient's jaw. The lathe pushes the rod out and then pulls it back in repeatedly to assist the shaping process. A tool now grips the implant while another cuts it to length. Then a computerized drill hollows out the implant and carves threads inside for attaching the ceramic tooth. In minutes, a solid metal cylinder becomes a hollowed and threaded implant. A robot now retrieves the implant from a colleague and transfers it to a cleaning station, and then over to what's known as a vision measuring system. Here, a camera takes pictures of the implant from all angles and sends the images to a computer for analysis. The computer confirms the dimensions are exactly right. Then the robot collects the implant and places it in a slot in a tray. Once filled with implants, a technician screws a mesh lid on the tray and slides it into a metal basket. This holds them steady for cleaning in a special washing machine known as a vapor degreaser. Inside, solvent vapors envelop the parts to clean off residual lubricant oils used during the cutting process. An implant is transferred to a holding device, which secures the implant for the next robot to press a plastic collar onto it. This collar is temporary. It will serve as a mask to protect the outside of the implant as the top undergoes a process of colorization. A robot places the implant upside down in a mild acid, and then an electrical charge is applied. Different colors will appear at different voltages to color code the part and indicate the diameter. The process is called anodizing. The masking collar now comes off. Then implants are taken to another tray and screwed in. This prevents them from falling off as machinery turns the tray upside down to immerse the implants in acid and anodize the exterior. This time the anodizing serves another purpose. It changes the surface to make it more porous. This will improve the bonding of the patient's jawbone to the implant. The implant sparkles in a solution as it undergoes a transformation. Here's the new porous surface magnified by a microscope. A robot transfers the dental implants to another tray. They're now ready for a final cleaning. They go into a tank full of hot, purified water. A generator sends high-frequency sound waves into the water, creating bubbles and waves that gently scrub the implants. After sterilization, these titanium dental implants are ready to take root in human jaws. The clinician screws the implant into the patient's jawbone and then secures a made-to-match ceramic tooth to it. Over time, bone will fuse with this artificial tooth, providing a long-lasting tooth replacement and giving the patient every reason to smile. Open wide.